Hi everyone, I'm Éric Guérin from the University of Lyon. In this video, I will present the gradient terrain authoring, a new framework for editing terrains. This is a joint work with the University of Cape Town, Strasbourg, and Lyon. This framework allows the authoring of the terrain effortlessly. We depart from the standard elevation representation of digital terrains in favor of its gradient. From a few user strokes, the user can instantly obtain landforms features in an intuitive manner. Altitude constraints can be defined as a set of hard constraints combined with gradient prescription that will influence the solver in the direction of the steepest slope. User control is central in this framework. Here are some examples of user editing sessions. The users effortlessly created a canyon, a cliff, a mountain range, and also our system also supports seamless copy and paste standard operations. Although a vast variety of terrain generation exists, only a few address interactive authoring. Our work allows for real-time interaction with intuitive control and can be compared to the work of EG2010 and Gain⁴. The procedural approach by Éric and colleagues in 2010 uses diffusion curves to propagate altitudes and slopes around constraints. The main drawback of this technique is that it generates terrain from feature curves and cannot be used for processing or enhancing terrains produced by other methods. Another texture synthesis approach proposed by Gain and colleagues in 2015 has very similar use case. It allows the user to place constraints that direct the texture synthesis algorithm. In comparison, our work provides a unified terrain representation. It is compatible with pre-computed topography and does not depend on examples like texture synthesis methods. The gradient of the elevation is central to our framework. The gradient combined with constraints implicitly defines the model. The elevation can be obtained by the reconstruction by solving a Poisson equation. Conversely, the gradient can be computed directly from the elevation. This dual representation allows us to utilize both standard algorithms operating in the elevation and gradient domain methods. Gradient-based algorithms are attractive in the scope of terrain modeling because the gradient represents the slope. Thus, we propose both local and global tools for authoring details or generating a gradient map from scratch. Let us review the formalism of our dual elevation gradient framework. Let's start with the easy part. We define the terrain as a 2D scalar field H, that indicates the altitude at every grid position. The gradient is a 2D vector field G computed from H. Since we operate on a grid, we use a discrete version of the gradient. Now let's continue with the reconstruction of the elevation H from gradient G. Since solving such an over-constrained system is not possible, we reformulate it as a standard Poisson equation. We compute the divergence of the gradient field and use it as the target Laplacian of H. We combine this differential equation with direct constraints that we can set anywhere on the grid, not only on boundaries. We implemented a fast and efficient solver that can be seen as half of a V-cycle in a multi-grid algorithm. Note that our compute shader implementation is available on GitHub. Constraints are essential in our framework. There are two different types. Gradient constraints are set by prescribing the gradient field. Those constraints are not always satisfied by the reconstruction process and direct the generation of the elevation. We call them soft constraints. Directlet conditions enforce the elevation at precise location onto the grid. They are always respected. Therefore, we call them hard constraints. Here you can see an example of the successive iterations of the solver that refine incrementally the solution. Using combinations of soft and hard constraints is convenient and effective to create landforms archetypes such as crests, cliffs, rivers, faults, or ravines. Hard elevation constraints are crucial, in particular for riverbed landforms, where it is important to guarantee that the terrain has a consistent flow direction without sinks. In other contexts, it is convenient to set soft constraints exclusively and perform an additive effect. In the fault effect that you can see here, two faults were superimposed to obtain a complex cliff. Compy and paste operations are usually performed in the gradient domain to obtain a seamless blending. Because the gradient representation is a vector field, we can modify it using 2D tensors. A 2D tensor will tend to bend the gradient in a given direction, guided by a theta angle that you can see here in this equation. As you can see, this has the effect of orienting the slopes in a given direction. Note that the tensor can vary depending on the position, guided, for example, by a user brush stroke. It is also possible to obtain complex combination of constraints to build high-level tools and brushes. For instance, a mounting brush consists of the creation of a gradient field around a crest line, like you can see here. This combined to a tensor-oriented noise to mimic erosion features here around the crest line. Here, our art constraints can be combined at different altitudes to obtain easily a massa effect. DEM are usually represented by images, which simplifies their manipulation. We can transpose this to the gradient using two channels of the image to represent the two components of the gradient here. This has the advantage to being able to use standard image algorithm, but applied in the gradient domain. We successfully applied this to super resolution, filtering, texture synthesis, and other machine learning methods. This illustration indicates that our solver can combine hard constraints with soft constraints. Here, we extracted the crest and riverbed lines of an input terrain that you can see here. Here are the extracted features. These lines were used to prescribe hard elevation constraints. In addition, we generated a tensor-oriented noise to simulate erosion patterns. This process allowed us to approximate the original terrain using very sparse information encoded in the hard and soft constraints. This example shows the effectiveness of the gradient representation of terrain for super resolution applications. It turns out that the super resolution is more efficient when performed in the gradient domain. In this example, we train a state-of-the-art super resolution method using gradient images. Experiments show that it's difficult to differentiate the super resolution output from the original elevation. This example illustrates the difference between learning from the elevation and learning from the gradient. The leftmost image shows the input river network. When using height, the synthesizer produces visual grid artifacts and smooth parts. Changing to the gradient domain removes the artifacts and yields sharper and more realistic landforms. Moreover, the gradient prescription combined with elevation constraints allows to post-process the model and enforce the river network to flow. Regarding the performances, our solver is real-time up to a resolution of 1000 pixels. Above this resolution, we get only interactive times. The memory footprint is limited and only gets higher than 1 GB when using very big maps of 8K by 8K. Here. Note that our implementation is available on GitHub. We tried to compare to the work by Hanaidi and colleagues in 2010. In their paper, they present this scene, authored in 45 minutes in their software. We tried on our side to author a similar scene and only spent 5 minutes to obtain the result that you can see here. Our approach shows less artifacts in the reconstruction because of the natural continuity of the solver. It also has a simpler direct interaction and more high-level tools that allows the inexperienced users to easily manipulate the tool. We performed 2 different types of validation experiments. First, we asked artists to test our framework and provide feedback on the effectiveness of the authoring tools. They could also report comments on the user interface. They found the tools efficient and intuitive and managed to create examples conforming to their intent. Moreover, artists encouraged us to display physical parameters in the interface such as altitude in meters or angles in degrees. We also asked non-artist users to author terrains according to simple text-based description within a 10 minutes time limit. The 3 images show several examples: a canyon, a volcano, and a mountain range. Almost all users pointed out that the tools were easy to use with a quick learning curve. So, in conclusion, we introduced a versatile model for terrain authoring that allows for high-level and intuitive interactive editions. There are several avenues for future work. In particular, terrain stylization and example matching brushes would be valuable tools to incorporate into this framework. We hope that this presentation demonstrated the effectiveness of gradient domain operators. I'd like to thank all the persons involved in this work that are displayed on this slide.